How does attention work? Attention is defined with this equation where three matrices Q, K, and V are multiplied. We also have the softmax and this division, but this is just to keep the number small. So what's the meaning of this equation? Well, actually, if we look at the encoder, we will see that we have attention in here. Before that, what we have is we will transform our input, which is text, into numbers using the input embedding, and we will also keep some information about the position of the words in the sentence, which word is first and which word is second, etc. After that, we will have 4 copies of the input. 1 copy will be left for later and 3 copies will go to the multi-head attention. And what this means that it's the same matrix that goes to the multi-head attention, and this is why we call this self-attention. So Q, K, and V will be the same. When it goes to the multi-head attention, it's called multi-head because we will do this multiplication using the attention. We will do it many times, and these will be done in parallel. Before this multiplication, there will be also a linear projection, but we will ignore this for now to make things simpler. Then what we have inside the scale dot product attention is this multiplication where we will multiply Q and K, and we said like it's the same matrix, so we will multiply Q by itself, but since due to size constraint this is not possible, we will need to transpose K. This is why we see the transpose in here. Then we will do the scaling by dividing by the root of the number of dimensions. Then while masking, there is no masking in the encoder, so this is nothing in here, this is just for the decoder. Then we will apply softmax to have numbers between 0 and 1, and finally we will multiply the same matrix Q, K, and V by V, which is, as we said, the same matrix again. So what's the meaning of this? To understand the meaning of this equation, first we need to understand the meaning of dot product. What is a dot product? Well, the dot product between two vectors A and B will give us the norm of A multiplied by norm of B multiplied by the cosine of the angle. So if we take the norm of both vectors equal to 1, then A dot B will give us the cosine of the angle between these two vectors. And here in our models, each word is a vector, so the cosine, this angle will be smaller if the words are similar to each other. So what this means is when we do the dot products, when we have similar words, they will have a higher dot product than non-similar words. Okay, now let's look at how to apply this in our multiplication. Let's assume we have this sequence. She made apple cake, and we would like to use attention on this sequence. So I will represent the words on 2 dimensions, which are food and tech. Well, actually this example is inspired by a very nice channel called Serrano Academy on YouTube, which also covers this topic in a lot of details, so make sure to have a look at it. Okay, so this is my matrix that represents the words in this sequence. So I have cake, which is food, and it has nothing to do with tech. So I will have my cake represented in here. Then I have apple. Apple can be fruit, but it can also be a tech company, so therefore it appears on both dimensions, and I will have it here in between. If I had the word phone, then phone will appear in here. And here I have my other words which are on some other dimensions that I cannot represent in here. So we said that in attention we will multiply the matrix using dot product with the same matrix, but due to size constraints we need to transpose it. So this is the transpose of the matrix. Now, if I do the multiplication, the dot product, what will happen is that I will do the dot product of the vector cake by the vector cake, which means that I will measure the distance between cake and cake. Okay? So this will give us the similarity between cake and itself. After that, I will measure the similarity between cake and apple. And if we continue like this, what we will get is the similarity between each word in the sentence and all other words in the sentence. So I will get this matrix where I have in the diagonal rather high values because each word is similar to itself. And then I will have other values that represent whether words are similar to each other or non-similar to each other. Okay, now after the first dot product, what we will do, we said we will divide by the number of dimension, the root square of the number of dimension. And this is because the dot product can grow too large, and this is because we have many dimensions in our vectors, so usually not only 3, but these will be hundreds of dimensions. After that, we will apply the softmax, and the softmax, it's like this, using this formula, it will transform all the values to values between 0 and 1 while preserving the order of the elements. So bigger elements will stay bigger, will be closer to 1. So what we'll have is something like this. Well, this is not exactly the softmax using the nth dimension, but actually what we will get is something similar to this, where we will have here in the diagonal values that are close to 1 because each term is similar to itself, and we will have higher values for words that are similar and lower values for words that are not similar. Okay, now we will do the third dot product. So we will multiply this similarity matrix with the very first matrix where we have the representation of each word on the 3 dimensions. And what this will give us, it will take in consideration the similarity between cake and all other words in the sentence, and it will multiply it with this, and what we will get at the end is what we see is now cake, which had 3 on food, has only 2.8. It's a little bit less food, but it is a little bit more tech. And how come? Well, the thing is that since cake and apple had some similarity, then apple attracted cake to itself. And if we continue like this, we will see that also apple was attracted by cake. So now apple is more food and less tech. So this dot product, what it does, it attracts similar words to each other. The more similar they are, the more they will attract each other. So if we look here in our figure, what will happen when I use the attention mechanism, apple will attract cake to it. So it will go more towards food. Also cake will be attracted by apple. But if I have the sentence new phone from apple, then what will happen is that phone will attract apple to itself. And from this, attention will give us the context. With this, we can understand the context of the word, or the word in its context. Okay, now let me go back to the multi-head attention. So before applying this dot product where we multiply the 3 matrices, there is something here which we call linear, which I ignored in the beginning to simplify the examples. Actually, what we have here is what is called projection or linear projection, and you can think about it as this. So Our words are points in space, and what we do before running the attention, we will project these on some dimensions, and we will do these projections many times, and after that, after each of these projections, we will apply the attention mechanism. And at the end, after applying this attention multiple times, what we will do is we will concatenate all the results together. Okay, so now let's look a bit into a small example how the encoder will work. Let's assume I have this sentence: she made apple cake, and this is my input. So the first step in the encoder is that it will transform my input into vectors, because I need to transform words into numbers so that I can apply the mathematical operations on them. After that, I will add some information about word position, which words is first, second, etc. And after that, I will make 4 copies of the matrix that I got here, where I have the embedding, input embedding, and the position. And 3 of these will go into the multi-head attention, and 1 we will keep for later. So we will go through the multi-head attention and we will get this result. After that, what we will do is an addition with, we will add it to this original one, and we will do some normalization. After that, our matrix, what we get here, will go through a neural network. So this is just a simple feed-forward neural network, and what we get as a result, we will add to it a copy of what we had before entering the neural network. So we will do an addition, and what we'll get here is the output of the encoder, which will go to the decoder. And actually the decoder also is very similar to the encoder. The only difference is masking, and hopefully I will make another video about masking.